Hello, everyone. Welcome to Wave Physics. I'm Chris. This will be the first of a series of videos that focuses on topics in wave physics, acoustics, and some music theory. And so this is an introductory video series to get you started and introduced to the topic, and I'll be your instructor. So without further ado, let's jump in. So what are waves? You might have an idea of what a wave is just based on everyday usage, but if you haven't studied wave physics or oscillations before, you might not know exactly what it is. So if you haven't studied this stuff before, take a moment to pause and think about what are some examples of waves. So one example of a wave is a guitar string. And when you pluck a guitar string, you'll notice that if you look really closely, you can see it vibrating up and down. And you can have different modes of vibration. And so you can get different kinds of waves depending on where you put your finger on the string, if you hold certain parts down. And these are waves. You can see the string moving up and down. Ripples in water are also an example of waves. And if you take that to a bigger level, you can think of tidal waves too. Those are very large things that come one after another. And here, even with ripples, you can see this kind of up and down pattern in the water as they ripple outward. So that's a wave. Earthquakes also produce waves. You have seismic waves, and so those travel outward from the place where the earthquake happens, and you get S waves, P waves, surface waves, and those all cause different movements in the ground and lead to different kinds of damages. Those are waves. You have sound waves. That's also another type of wave. And you also have electromagnetic waves, or like light, X-rays, infrared. And the last two, sound and electromagnetic waves, might seem a bit strange to you because they don't really look like, you can't see them as waves. You don't see something that looks like it's going up and down. With sound, you hear it. With electromagnetic waves, you can see visible light, but you don't actually see the wave characteristics of it. So from this, you might guess that wave has something to do with like a pattern that looks kind of curvy and goes up and down. But waves that look like this aren't the only type of waves. You can have waves, and these are different examples of sound waves. You can have waves that have different shapes, or what we call waveforms. And so if you have sound waves with different waveforms, they will actually sound different. So you can have more than just a curvy sinusoidal wave. You can have square, triangle, sawtooth waves, and they'll all sound different. And I'll play this video right here. It's a bit loud, so you can hear that. That's a sine wave. That's a square wave. A triangle wave. And so this is a sawtooth wave, and you can see that they all have different acoustic characteristics. But these might not fit your definition of what a wave is. So what really is a wave? What's the definition of a wave? So one definition of a wave is a propagating dynamic disturbance that transfers energy through a medium from one point to another. Makes perfect sense? No, probably not. So let's take a look at what this really means. So a propagating dynamic disturbance. So let's look at this example of a wave that passes along a string, rebounds off the ends, and comes back. And the string is fixed at both ends. So the ends cannot move, but the middle of the string can move. And so you can see this wave that travels across and travels back because these parts in the middle are free to move up or down. And so a propagating dynamic disturbance. So a dynamic disturbance is whenever the wave passes through a point, those pieces of the string are moving up or down. The parts that, if the string were at rest, the parts that wouldn't be affected by the wave, they're not moving. They're just like, they're stationary. That's static. That's kind of an equilibrium, as you can think of it, not a dynamic disturbance where they're moving because they're being disturbed by the wave. And it's propagating because the wave will travel back and forth across the string. And it transfers energy because when the wave passes through a point, the parts of the string that move, they increase in energy, in kinetic energy. And so something important to note is that you don't actually have pieces of the string that are moving left to right. Instead, each little piece of the string is just moving up or down when the wave passes through it. And so what happens is, like, when this part of the string moves up, that pulls up the part of the string next to it, which pulls up the part of the string next to it. And so you get a transfer of energy from one element of the string, one little piece of the string, to the next, which transfers to the next. And that's how the wave travels from left to right and then back, because each piece of the string will transfer that energy over to the next piece of the string. And so there are different types of waves. There are two main types of waves. One is a transverse wave, where the oscillations are perpendicular to the direction of propagation, and one is a longitudinal wave, where oscillations are parallel to the direction of propagation. So if we go back to the earthquake example, if we look at S waves, these have the oscillations going up and down on the z-axis, whereas the direction of propagation is down the x-axis. So this is an example of a transverse wave because the oscillations up and down are perpendicular to the direction of propagation, which is this way. On the other hand, if we look at the P waves of an earthquake, this is a longitudinal wave. You notice that the oscillations happen in the same direction as propagation. You'll have the parts that compress and then come back, and they'll move, these little elements will move forward and back and forward and back, whereas here they also up and down and up and down. So this might be a bit harder to kind of visualize because you might think more of a transverse wave when you think of a wave, but these are also waves, these longitudinal waves. And so sound is an example of a longitudinal wave. And this diagram shows that, and it can be really hard to wrap your head around this at first, but this is what is happening to the air particles when a sound wave propagates. So if you look at, this is a piston that's moving back and forth to generate a sound wave, and you can see this pattern, that these, particles there seems to be some propagation of this wave to the right. But if you look really closely, and if you look really closely at these red dots, each particle is actually just moving back and forth, just kind of in a little place. You don't have particles that are moving all the way from the left to the right, even though it looks like there's a pattern moving from the left to the right. Instead, each particle transfers energy from particles next to it and then to other particles. So energy gets transferred in this direction from left to right because of particles bumping into each other and transferring that energy. And so that's how you get a wave, a propagating dynamic disturbance. The particles are moving, so that's a dynamic disturbance that transfers energy from left to right. So how do we model waves mathematically? We can see waves, but how can we, analyze them? And so one very common way to analyze waves is to model them as a sine wave, a sinusoidal wave. And so you can do that with the sine or the cosine functions. And for the next few videos, I'm going to assume that you're familiar with these functions. If you're not familiar with these functions, if you haven't taken pre-calculus or trigonometry, the very basic gist of it is that they are functions that range from 1 to -1, and they have this repeating shape where sine and cosine are the same curve, and they're just shifted by pi over 2. And so when x equals 0, sine will be 0. And as x increases to pi over 2, it goes up to 1 and then decreases down to -1 and then comes back up to 0. And so every time x increases or decreases by pi over 2, the curve will go back to where it started. And so if you don't have experience with these, I strongly suggest that you look at some external resources like Khan Academy, or some textbooks can help you learn the sine and cosine functions better. This is really important for wave physics. So that's the introduction. Let's briefly go over what we're going to cover in the next couple videos that I'll be doing. And so there are 3 main topics in wave physics that I'm going to be covering. One of them is oscillations and wave physics. And this is the very mathematical part of it. This is the modeling with graphs, equations, functions, what happens when you add waves together. And so that's one topic. That we'll be exploring that first. That's the very nitty-gritty side of it. Second is acoustics. And so this is kind of the applications to sound. And so we'll talk about instruments, different perceptual phenomena of sound waves and how they travel. And the last one is a bit of a step back from physics, and it's to something quite different. It's music theory and aural scales. And so sound is a form of waves. And so we're going to be looking at music, and I want to be focusing on how to kind of train your ear to recognize different patterns in music. And so this is a very kind of interesting combination of physics and of music, which are pretty different fields at a first glance. So as a brief overview of the topics in topic 1, we're going to talk about simple harmonic motion and terms like amplitude, period, frequency, if you've heard that before. And so this is something that's very commonly taught in physics classes. We're going to talk about how you can represent oscillations with equations and graphs using the sine and cosine functions. We're going to talk about superposition and interference, which deals with what happens when you add 2 waves together. If you have 2 waves on a string, what happens when they meet each other? They combine to form a new wave. What does that new wave look like? We'll talk about properties of transverse waves on a string. So those include more complicated things like average power, which is the rate of energy transfer. And then we're gonna talk about some calculus too, and we're gonna be doing some derivations and integrations of sine and cosine functions using the chain rule. And so if you haven't had calculus experience yet, I'll be covering it briefly on how to work with the sine and cosine functions in future videos. But for a conceptual introduction, I strongly recommend that you watch 3 Blue 1 Brown's videos, The Essence of Calculus, chapters 1 and 2. And so those are 2 videos, each one is about 20 minutes, and they give a really good introduction to what calculus is on a fundamental conceptual level. For acoustics, we'll be covering things like the motion of particles in a sound wave. We saw that complicated diagram of particles in the longitudinal wave moving back and forth as the sound wave moved from left to right. So we'll take a closer look at that. We're going to look at properties of sound waves, and so that includes, frequency, amplitude, intensity, other terms that you might hear being thrown around. We're going to talk about certain acoustic phenomena like resonance, interference, and beats, and these all have very physical underpinnings to them, and which can then lead to things that we experience in real life. We're going to talk about the absorption and transmission of sound. Some frequencies of sound can travel better than others in certain conditions. Some materials can absorb some frequencies of sound better than others. We'll talk about that. And we'll also talk about some instrument mechanisms for producing sound. We'll talk about the ways that flutes, wind instruments and percussion instruments and string instruments can produce sound, and the different ways that you can modify the amplitude and the frequency for those instruments. And the final topic for music theory and aural skills, I'm not going to talk a lot about, the very basics of music, how to read notes on a staff and stuff like that, because that's something that you can really learn anywhere online. But instead, I'm going to try and focus more on the kind of the aural side of things, the hearing part of it, and see if I can get you to train your ear to listen carefully and identify things. And so some of the things we'll cover, I'll cover a little bit about tuning systems and frequency, and the different tuning systems that we can use to represent pitches. I'll talk a bit about notes, solfege, keys, scales, and modes, and how you can try to identify modes or certain scales based on just listening to them. I'll talk about time signatures and tempo, and how you can identify time signatures while listening. Intervals, chords, and chord progressions, and how you can hear those out as well. And also reading and analyzing musical scores and listening to and analyzing audio samples. And so we'll see how we can take these concepts and apply them to actual music and what we can get from those pieces. And so you don't need to be a trained musician, or you don't have to have perfect pitch or anything. Nowhere will I assume that you have perfect pitch, but it is good to develop a sense of relative pitch. That is, if you have one pitch and then another pitch, you hear another pitch, you can use that reference pitch to figure out what's the interval between those two notes. And so that's a brief overview of the topics that I hope to cover. I might cover some of them more, or might not get to some of them, depending on what I have time to focus on. But that's a good framework for the overall outline of wave physics. So that's all for the intro video. And if you want to get a head start on topic 1, some things you can read are Giancoli's physics textbook. Chapter 11 talks about oscillations and waves. And then Halliday Resnick's physics textbook also talks about waves in chapter 16. And the difference between the two is that Giancoli's textbook, it doesn't focus on calculus, but Halliday's and Resnick's does. So I prefer Halliday's and Resnick's because I think it gives a better conceptual understanding. But if you don't have experience with calculus, then you might find Giancoli more accessible. And then also for video 1, I strongly recommend that if you don't have a solid background in math already, that you review trigonometric functions like sine and cosine, and also grasp a basic understanding of calculus, and maybe see if you can try to review or learn how to take the derivatives and integrals of sine and cosine with the chain rule. So that's all for today. Next time I'll start covering oscillations in wave physics and the math behind it. So I hope to see you all then.